Okay, welcome back. We were talking about the branch and bound algorithm, and in our previous lecture we started learning the details of this algorithm. The algorithm actually starts by relaxing the integer restrictions of the problem and obtains an integer linear program, and then obtains a linear program and then solves this linear program, and depending on that solution it comes to a conclusion whether to stop or to continue by adding some new constraints. Okay, and this is the main idea of the branch and bound procedure. So in our previous lecture we solved one example, and in that example let me show you the final solution of that example. So we started our solution with the root node, so-called the root node of the branch and bound tree. So this shape is called branch and bound tree. Okay, because it looks like a tree. Actually, in a tree we have this branching towards the top, but here it's an upside down tree. The root is at the top. Okay, and usually we also say that, okay, in branch and bound tree, this is, for example, level 0, the branch or the nodes at level 0. Then these are the nodes at level 1, and then we can continue even further for level 2, level 3, and etc. So the levels goes deep into in these branch and bound trees, and we number each of these levels, and these levels we will make use of them later while calculating bounds. Okay, so we started from this initial relaxation of the integer problem and solved it. In this example, we solved it using the graphical solution method and obtained this solution. And since x1 and x2 values, actually it is enough only if one of them is not integer, we should branch it, we should concentrate on that decimal value, non-integer value. And here we said that, okay, x1 is 3.75, so it cannot take a decimal value, it should be integer, but the best is 3.75. So let's divide the problem into two parts by considering first the values of x1 which are less than or equal to 3, and also as a second problem the values of x1 which are greater than or equal to 4. So we include these two into our original problem as constraints, and we obtain two new problems. The first one is LP2, the second one is LP3. We name them, and in LP2, when we solve this linear program with this additional constraint, we obtain this solution, and we say that, okay, since x1 and x2 all decision variables are integers, we don't need to continue anymore. This is the best integer solution of this part of the problem. So we fathom it, we terminate it. And the reason of fathoming is fathom by optimality, we call it. Okay, then we go to the other problem. Without solving the other problem, we cannot say this is the best solution of our original problem. We can only say that this is the best solution of the left-hand side, on the one side of the feasible region. But there remains the other side. But as we discussed this in our previous lecture, since the best solution can be at most 23.75, this is an upper bound, and the coefficients of the objective functions are both integers, then the best integer solution can be 23, at most 23, and we already have a solution which is 23, so we don't need to consider this right-hand side anymore because we already obtained a solution which is equivalent to the upper bound. So we fathom this part as well, and the reason for fathoming is we fathom by bound. You can ask me, okay, but if we don't do that reasoning, can't we continue solving this part and continue and find the best integer solution on this? Yes, you can do, but the idea of branch and bound is, remember, in complete enumeration that we talked about in our previous lecture, we try all possible combinations of these decision variables, and it takes a lot of time. And in branch and bound algorithm, we want to get the solution as quickly as possible. So if you go to this right-hand side and solve it, it will take time. But if you do this reasoning and without solving that problem, you eliminate that, then you will save some time. In some questions, that time that you eliminate would be very significant. Okay, so it means that whenever you can do such a reasoning, you have to do in branch and bound algorithm. It is one of the important properties of branch and bound. Now, when we consider this solution of the example, there are actually two questions you may ask. The first one is, in LP1, okay, when we solve LP1, the solution, the value of x1 was 3.75 and the value of x2 was 1.25. Both of them were not integers. We selected x1 and said that, okay, I'm going to include one constraint as this one and the other constraint as this one and continue. But why didn't we consider x2? Because it is also not integer. Can't we branch this procedure on x2? Is it a condition that we should always branch x1? No, of course not. You could do the same thing. You could solve the same problem by branching on x2. And in this case, the constraints that you need to add to the model are x2 less than or equal to 1 and x2 greater than or equal to 2. So this is 1.25, the smallest integer and larger integer than this one. So you need to include these two constraints and solve it. And actually, this is a homework for you, for your trial. Solve the same problem by branching on x2 instead of this x1. Solve it by using x2 and try to understand what's going on. The second important question is this. Okay, we decided to solve. We decided to add constraints to x1. x1 less than or equal to 3 and x1 greater than or equal to 4. But now we have two LPs. We named them as LP2 and LP3. Okay? So what we did is we selected LP2 and solve it first. And then we moved to LP3. But can we first solve LP3 instead of LP2? Can't we first solve LP3 and then move back to LP2? Of course you can do. And in all these alternatives, you will get exactly the same optimal solution. But the procedure itself, the path to the optimal solution will be different. Okay, the computations will be different. So let's solve the same problem using the second case, starting from LP3 instead of LP2. Okay, so this is the problem where we have this additional constraint, x1 greater than or equal to 4. Remember the feasible region? Okay, it was something like this, and we divided this into two parts, like this and this. So x1 less than or equal to 3, x1 greater than or equal to 4. Now I'm considering this right-hand side, okay, and trying to find the best integer solution on that right-hand side. Now the feasible region on the right-hand side is this triangle over here. And my objective function is to improving direction is this one. And if you move in that direction, we find the best solution, best integer solution to be these values. Okay, x1 equal to 4 and x2 equal to 0.83. Actually, this one is the optimal solution on the right hand side. Okay, now look, x1 is integer. Very good. This is what we want. But x2 is not an integer. It is 0.83. So what can we say? Can we stop the algorithm? Can we say that we found the integer solution, best integer solution on the right hand side? No. Can we just round this down or up and find the integer solution, optimal solution? No, of course not. What we need to do is, okay, we started from this LP1, remember, then we branched so that x1 less than or equal to 3, x1 greater than or equal to 4. This was LP2, but we considered LP3 instead of LP2. We started from here, we solved this problem. We haven't solved this problem yet. We will consider it later. And here we see that x2 is not integer. So what should I do? I should consider this x2 and now say that, okay, x2 less than or equal to 0, smaller integer, and larger integer, and x2 greater than or equal to 1. And now I have two new integers. What are they? LP5 and LP6. And I need to consider these to find the best integer solution of this part. So when we include these two constraints, we obtain LP4, LP5. Now look at this. At this step, I haven't solved this problem yet. I haven't solved this problem yet, and I haven't solved this problem yet. The problems that we haven't solved are called open branches. Okay, so these branches are still open. I haven't solved them, I haven't branched them, or I haven't terminated them. The branch and bound algorithm stops when there are no open nodes or open branches. Okay, since there are 3 open nodes, I cannot stop the algorithm. I have to continue. It means that I need to select one of these LPs next and solve it. Which one should I select? Again, we will discuss this later on, but in this example, let's just select one of them randomly, and we select randomly, arbitrarily, this LP5, okay, as the next one. It is just arbitrarily, but let's consider, this is also important. In LP4, what is the problem? It is on top of LP3. Remember, in LP3 I included this one. Okay, so this is LP3, and then in this LP3, for LP4 I include this constraint, and for LP5 I include this constraint. So what does it mean? I have this original model subject to I have these constraints. In this LP3 I have this additional constraint, and in this LP4 I have this additional constraint. Okay, so I keep this one, plus on top of that I am adding this new constraint as well. So I have this new LP now with 2 new constraints. So at each branch, actually I am adding a new constraint to the problem. But this is the problem on LP4. On LP5, what do I have? I have this maximize Z subject to these original constraints. And here again I have x1 greater than or equal to 4. But on LP5, instead of this one, I have this, x2 greater than or equal to 1. As you can see, the set of constraints differs for each LP. Okay, now we are considering this problem in LP5. X1 is greater than or equal to 4, which means that we are considering this region, and X2 greater than or equal to 1. Look, this is 1, and X2 greater than or equal to 1 is this one. So what is the solution to this linear problem? This this shaded region and this constraint has no common parts, has no intersection. It means that this LP is infeasible. LP is infeasible. This LP5 is infeasible. What does it tell us? It tells us that if LP5 is infeasible, then if you include this integrality, if you want to find the best integer solution in that region, it is also infeasible. You cannot find an integer feasible solution here. Remember the use of relaxations, proving infeasibility by relaxations. If the LP relaxation is infeasible, then the integer is infeasible, integer problem. But look, I am not considering the original problem now. I am only considering one part of it. I am on this right-hand side, and plus I included this one. And is there any integer solution here? No, of course not. Okay, so if there are no integer solutions, if there are no, the LP is infeasible, then we fathom. And the reason for fathoming is by infeasibility. So whenever we fathom a node, we always include the reason. Fathom by infeasibility. Okay, it means that LP5 is infeasible. Then I need to continue the others. There are still two other open nodes, which are LP2 and LP4. I haven't considered them yet. So this is now the current state of my branch and bound tree. I started from LP1, solved it, and I branched on X1. Then arbitrarily I selected this one, okay? And then I found that X2 is not integer and branched it into 2, and I selected this side, and I found that this LP has no feasible solution, so I fathom this part. Now this one and this one are open. We don't know this solution yet, okay? So this LP2 and LP4 are open. Which one should I select? Okay, again, let's continue arbitrarily from this LP4. When we consider LP4, we include this X2 less than or equal to 0 into the model. And look, this is the right-hand side, X1 greater than or equal to 4. And I include this constraint, X2 is less than or equal to 0. Okay, so as you can see, the intersection here is this line. The feasible region only is this line segment. And when you solve this problem, you find that the optimum LP solution is this corner of the line segment, which is X1 is 4.5, X2 is 0. Now you see, X1 is not integer anymore. Can we fathom this? Can we fathom this for some reason? The reason for fathoming, there are several reasons for fathoming. Okay, one of them is finding an integer solution, fathom by optimality. One of them is proving that it's infeasible. One of them is having a bound. But in this case, we have none of them. Okay, it is not integer. It is not an infeasible solution. And we don't have a bound at this step to fathom. So it means that I need to branch on this one more time. And on which variable should I branch? I need to branch on the X1 because it is the decimal value. It is the non-integer value. Okay, just a minute. Okay, so now when I branch, I obtain two new LP solutions. Okay, these two new problems, LP6 and LP7. Why I have these two? Remember, in LP5, this x1 appeared to be 4.5. Now I need to branch it into two. So the smaller integer is 4, the larger integer is 5. So I need to add that this x1 is less than or equal to 4, and on the right hand side I need to add x1 is greater than or equal to 5. Okay, so when I add this one, I call this as LP6 and the other one as LP7. So these are just numbers. And in LP6, what do I have? The original problem plus x1 greater than or equal to 4 at the first branch. Okay, plus x2 less than or equal to 0 in the second branch, plus x1 less than or equal to 4 in this branch. So I include 3 new constraints. Okay, now when you compare these two, when you look at these, observe these two constraints, x1 is greater than or equal to 4 and x1 is less than or equal to 4, means that x1 is exactly equal to 4. Okay, you can just find the value of x1 to this LP6 directly. And on LP7, what do we have? x1 greater than or equal to 4, x2 less than or equal to 0, x1 greater than or equal to 5. And remember, in our feasible region, okay, we had this right hand side over here. So this was the value of 4 and 5 was here. So this was the small triangle on the right hand side, and when you include this constraint x1 is greater than or equal to 5, you see that this triangle and this constraint has no intersection. It means that this LP7 is infeasible. So since LP7 is infeasible, we fathom it and we don't continue on that side. We return back to this LP6 and we find this solution. And as you can see in this solution, x1 is 4, x2 is 0, and z is 20, and this is an integer solution. And since it is integer, we fathom it. The reason for fathoming here is by infeasibility. The reason for fathoming here is by optimality. Okay, we found an integer solution. This is our first integer solution. And let's have a look at this branch and bound tree, what we have now. Okay, we started from this LP1, we included this one and moved to LP3. We went to this one and we have seen that this is infeasible. We fathom it, we return back to this one, solved it, and we saw that x1 is not integer. We branched it. We went to this side and found that x1 is greater than or equal to 5 is infeasible. So we terminated, fathomed it, and it is because of infeasibility, we return back to this solution and we solved it, and we found that x1 and x2 are both integers. That's why we fathomed it. And we find an integer solution. But is this the optimal solution? We can't say that this is an optimal solution because we haven't evaluated this yet. LP2 must also be evaluated. Okay? Before evaluating that, I cannot say that this is the optimal solution. But what can I say? This value x1, x2 are both integers. And for a maximization problem, I found an integer feasible solution. Okay, integer feasible solution for a maximization problem. It means that my integer IP should be optimal solution, optimal objective function value should be greater than or equal to this feasible solution, which is 20. Okay, so the optimal objective function value will be larger than or equal to 20. And of course, we don't know if it will be 20, 21, 22, but we only know that it will be larger than or equal to 20. Okay, after solving LP LP6, was it LP6? Yes, after solving that LP, we obtained an integer solution, but we cannot say that it is the optimal solution. And there is still one open problem, one open node, which is LP2. And I need to return back to that LP2 and solve that LP. And remember, what was that LP? This was the original LP1. And on this LP1, I have included this constraint. In LP2, I only have this constraint. The others that I have included on the other side, all these constraints are valid for this side. On LP2, I have only this constraint. Okay? A constraint that I have included here does not have an effect on this side. Okay? The constraints that I included on a branch affects only the branch following that branch. Okay? So if I, for example, add this constraint x1 greater than or equal to 4 to here, then this constraint affects all the branches downwards. So for an LP here, I also have this x1 greater than or equal to 4. I have x2 less than or equal to 0. All of them will be included here. But these will not affect the constraints on the other side. Okay? So now when we solve this LP2, we obtain this solution. X1 is equal to 3, X2 is equal to 2, and Z is 23. And since this is an integer solution, we fathom by optimality. Sometimes instead of optimality, we can call fathom by integrality. What does it mean? Finding an integer solution. Okay? And then we have, initially, we found an integer solution with a value of 20. This was an integer solution. This was the best integer solution that I found until this time. But now I have a new integer solution. I need to compare them with each other. Because at the end, I will report the optimal solution, the best integer solution. And I should be able to say that, okay, this is the best integer solution. So I need to keep track of the best solution. And until this LP2, until solving this one, the best integer solution was this. But then I solve this problem and obtain this solution, and I need to compare them with each other. The problem is a maximization problem. It's important. And for a maximization problem, 23 is better than 20. So it means that this new solution is better than my old solution. So I am going to update this best solution. Now it is not 20, but it is 23. This is the best solution that I know until now. And since it is integer, I fathom this LP2 as well. And when I look at the branch and bound tree, there are no other problems. We call these sub-problems because we start from the top level and then we divide it into some smaller problems, and we divide it into some problems. We call these problems as sub-problems because we divide the feasible region into two parts, then we divide it into further two parts, and etc. Each one of these problems are called sub-problems. Since all sub-problems are fathomed, all nodes are fathomed, we stop. And when we stop, the best integer solution that we know is the optimal integer solution, which is x1 3, x2 2, and z is 23. Okay, now this is the complete branch and bound tree. We started from LP1, we had two new solutions, and as you can see, this is number one. We first evaluated this one, and then we have two new LPs, and we selected this one, so we name it as the second node. Okay, so we don't just say that, okay, this is 1, this is 2, this is 3, and etc. These numbers of the nodes tell us the order of evaluating these nodes. We first evaluated this one, then we moved to this one and evaluated then and branched it into 2, and then we moved to this one and evaluated that one. So this is 3. Then we fathom it and then return back to this one and evaluated that, so it is 4, and branched it, and we moved to this one and evaluated that one, so this is node 5. We fathomed it because of infeasibility, and we moved to this one and evaluated that, so this is node 6. And then we found an integer solution, that's why we fathomed it, and we returned back to this and evaluated that, and that is node 7 now. As you can see, this is not node 2 or 3, this is node 7 because it is evaluated in the 7th order. And we found an integer solution, that's why we fathomed, and as you can see, there are no other open nodes. And we obtained exactly the same solution with the previous one. What is the previous one? The previous one is this. Look, when we first solved this problem, we first selected this LP2 and evaluated that one. We get an integer solution, and then we moved to the right hand side, and because of this bounding, we just eliminated this side, and just in 2 steps we found the optimal solution. But when we solve the same example in a different order, instead of selecting LP2, if we select LP3, as you can see, we have now a very larger branch and bound tree. So large tree means it will take more time to find the optimal solution, but the optimal solution is exactly the same. It is 23. But the first one takes very small amount of effort and time, but the other one takes a lot of time and effort. But which one should I select? I mean, when I solve this LP1 and branch it into 2, there are 2 open problems. Is there a method to identify which one is the best? No, unfortunately not. So it is just your chance. You can select LP2 and it may take longer and longer and longer, but if you decide on LP3, maybe you would find it in only a few steps. But, or vice versa, you cannot know at this stage, okay? But there are different strategies that we will talk about selecting the next alternative. We will discuss this later on. Okay, now we have solved an example using the branch and bound algorithm. We will do more examples. We will solve more examples. There are more details of the algorithm, of course, but it's a good time to have a look at the solution procedure or the algorithm of this branch and bound algorithm. At the beginning, I gave you this general scheme of the algorithm. So in step 1, we are relaxing the integer problem and find an LP and solve that LP, and depending on that LP, we add spatial constraints, and those spatial constraints that we included, what are they? For example, x1 less than or equal to 3 or x1 greater than or equal to 4. These are the constraints that we include in branch and bound, okay? So if you return back to these general steps, now it should be more clear. But now let's have a look at more detailed steps of the branch and bound algorithm. And these steps are given for a maximization problem. Okay? So what we do? In step 0, so when you have an algorithm, usually we start with step 0, which is the initialization step. And we set the objective function value to be equal to -infinity. Look, for a maximization problem, we set the initial objective function to be -infinity. What does it mean? When you start a maximization problem, solving maximization problem, initially you don't know any integer feasible solution. You don't have this solution. So you start with the worst possible solution. For a maximization problem, the worst possible objective function value is minus infinity. We start from this one, and during the branch and bound tree, when we find new integer solutions, we update this. And this is the iteration counter I, we set it equal to 0. Okay, in the first step, what do? We start with the LPI, which is LP0, the first LP. Actually, in the previous example, we started the LP from 1, LP1, LP2, LP3. But here in this algorithm, we start from LP0. LP0 is the first LP. It is just numbering. Don't be confused, okay? You can start from 0, you can start from 1. But usually, since the top node is named as the root node, we name it as node 0, and the first LP that we are solving is LP0. Okay? So what do? We select LP0 as the next sub-problem to be examined and solve it. This is the first LP relaxation, original LP relaxation that we have at the top. Okay? This is LP0. And then try to fathom this. Okay? Is there a reason? Solve it and try to fathom it. Is there a reason for fathoming? So there are actually 3 reasons for fathoming. We can fathom because of a bound. So we obtain here a z value, okay? By solving this LP relaxation, we obtain a z value for the LP, not for integer, a z value, and compare this with the best integer solution that you know until now. If the best integer solution that you know is better than this one, then you don't need to continue anymore. You will not be able to find a good solution. So you can fathom by bound. So this fathoming by bound is very critical. You will get the idea when we solve examples on this. Okay. Let's continue with the others, and it will be more clear when we solve examples on this. But actually, you can consider in our previous example, in the first case when we solved LP2, we identified that there is no reason to solve LP3 because we already found the best possible integer solution. So we fathomed this side. That was because bound, okay? We fathomed because of bound. The second reason, okay, assume that we could not fathom because of this bound. We can try to fathom because of obtaining an integer feasible solution. When you solve this LP relaxation, if it is already integer, then you can stop because of this integer solution. If that's not the case, you can try another alternative. If this LP is already infeasible, then you don't need to continue, you can just fathom. So these are the 3 reasons. When you solve an LP, if it is infeasible, you fathom it. If it is integer, you fathom it. If the objective function value after solving it, if the objective function value is not better than the best integer, you fathom it. Okay? And when you fathom a node, you may have 2 cases. Okay? You fathom because of this integer, finding an integer solution. If you fathom because of this reason, you fathom because of finding an integer solution, then you need to compare it with the previous solution. Look, what was the previous objective function value? Initially, it is minus infinity. Now, assume that we solve this problem and we obtain an integer solution, x1, x2, they are integer, and this is the maximization problem, and the z value is 20. So you compare 20 with this minus infinity. Which is better? For a maximization problem, 20 is better. So if it is better, you update this. So this becomes a lower bound for you. The optimal solution will be at least 20. You understand it. And if there are no other open nodes, if all subproblems are fathomed, you stop the algorithm, and the best integer solution that you have until that time will be the optimal solution to your problem. Okay. The other case, if you fathom, if you cannot fathom this case, this node, okay, if you fathom this node, and then you look for other open nodes. If there are no other open nodes, then you stop. But if there is at least one open node which you haven't considered that yet, you need to move to that one, okay, and try or solve that LP and continue. Otherwise, if you cannot fathom this LP, now I need to branch it, okay? If I cannot fathom it, I have to branch it. In order to branch, what should I do? I need to include two constraints, okay, to the problem. So this is the node, and assume that I have one decision variable x1, which appeared to be, let's say, 4.2. Okay. Now I know that this 4.2 should be great. I mean, in this interval between 4 and 5, there will not be any solution. So this part simply says it. If you find 4.2 as LP, the smallest integer and the smallest integer plus 1, which is 5, in this region, there will not be any integer solutions. So we are going to add a constraint saying that this x1 is less than or equal to 4 as the one branch, and x1 is greater than or equal to 5 as the other branch. So these equations and etc., don't be confused with them. We already learned it, how to include these. Okay, then it means that we include these two, x1 less than or equal to 4 and x1 greater than or equal to 5, and we obtain two new LPs, and we increase our iteration index, and return back to step 1. And step 1 says that select another LP, let's say this one, solve it. After solving, try to fathom it by integrality, by infeasibility, or by bound. If you fathom it, move to another one. If you cannot fathom it, branch it. This is the algorithm. And try all open nodes one by one until you get the optimal solution. Okay, so this is the branch and bound algorithm for a maximization problem. So what about a minimization problem? What will be changed in a minimization problem? And if we have some mixed integer problems instead of pure integer ones, all decision variables are integers. If we have a mixed integer problem where some decision variables are integers, some are not, what can we do? So let me answer the first question. What about a minimization problem? This is the algorithm for a minimization problem. Exactly the same algorithm, but there are a few differences. First of all, for a minimization problem, the red ones are the differences from the previous one, red highlighted ones, okay? These are the differences. So the first difference is this. In step 0, z equals to minus infinity. For a maximization problem, we set it to the worst possible case, which was minus infinity. But for a minimization problem, the worst possible thing is plus infinity. So we set z equals to plus infinity for a minimization problem. We start from here. Then again, we select the next LPI and we solve it. And if we cannot find this LPI, cannot yield a better objective function value than the current lower bound. Okay, is it the lower bound? Now it is upper bound. Okay, it is changed to upper bound. Then we fathom it. If LPI yields a better feasible integer solution than the current upper bound, then we can fathom it. And if LPI has no solution, we can fathom it. Then if LPI is fathomed and a better solution is found, update the upper bound. So now in a minimization problem, we are finding an upper bound by an integer solution, not a lower bound. So every lower bound is changed by upper bound in the minimization case. All others are the same. And the branching procedure is exactly the same. Okay, so what is the difference? For a minimization and maximization problem, you should be careful with the bounds, whether it's an upper bound or a lower bound. Okay, that's all. And the thing is, here, if it's a mixed integer programming formulation, you don't consider the continuous variables in branching. You only consider the integer variables. We never branch a continuous variable. Okay, never branch a continuous variable, only branch integer variables. That's it. And these are the steps of the algorithm. So we will solve examples on branch and bound algorithm and also learn how to implement branch and bound algorithm when we have binary decision variables in our next lecture.